Hi, my name is John Shu. I'm the Simulation Services Director for Maya HTT. I was wondering why my talk was sandwiched between the two AI talks, and now I'm thinking it was just so I could rebut everything that Renee was saying about the simulation team and regain some of our honor. But anyway, a little bit about myself. So I've have engineering experience for 18 years. I've done, primarily through my work, done structural, thermal, and fluid dynamic analysis in multiple industries for multiple companies. I worked for companies small, large. I did the engineering startup thing for 6 years. And I've been involved in every step of the engineering design process, from conceptual design all the way to manufacturing and delivery of product. And today, what I want to talk about is a very initial stage of where the design and simulation collide at the very beginning of the concept. So if we look at the normal design analysis, design simulation process, we'll often start with the designer releasing an iteration of their design, send that off to the simulation team, and simulation is often a bottleneck. It's hard to do, takes a long time to do it right. By the time the simulation results come back, you're already on iteration 3, 4, 5. You might, kick off the latest iteration for simulation. And that cycle can continue for a while. This isn't really a communication problem even all the time. This is just because simulation takes time to do correctly. Can be a communication problem as well. I know I had an example where I was working on a project, doing the simulation for about a month, come back with the results. When I came back with the results, they told me that the design actually changed about 2 months ago, and nobody told me. So what do you do in that scenario? Well, you make a tough choice if you either decide if your simulation was good enough then, or you have to go kick off this whole cycle again. But if we think about it for a second, what if I could take some of the insights of simulation? I could use those to actually feed into the first iteration of the design. And then from there, each successive iteration, I could use some simulation insight to feed into that. You're going to get a much better product. You're going to be able to do that. You're going to be able to look at more concepts. You're going to be able to get a more robust product, and you're going to get it right the first time. And that's kind of what I want to talk about today, is how you can accelerate your design process by taking advantage of some of the tools and methods that are available now that you can put in the hands of the designer up front. And that's what we're calling simulation-driven design. So that's going to be, before I talk about that a little bit more, I actually want to talk again about some of the benefits of it. So the Aberdeen Strategy and Research Group had done a study and showed that companies that have actually fully embraced this simulation-driven design concept, they were able to see a reduction in the number of physical prototypes they had to do. They were able to reduce the engineering change orders after they sent a part to manufacture. That just means they got the part right the first time, didn't send it out there to manufacture and then figure out there were problems. In addition, they're able to more often meet their cost targets and also speed up their development as well. Now, those are some pretty excellent improvements, and actually for something that I think any design team can implement rather easily. Some of the tools, some of the methods we've talked about today, they all help. Some of them are harder to implement than others. This one's actually really easy and often built in already to a lot of the design tools you already have. And to help walk you through this and explain a little bit what simulation-driven design is, I want to talk through an example workflow for you. We try to come up with something that I think's fairly realistic workflow that'll explain to you some of the tools, some of the methods, and how you could integrate this into your design process as well. So some of the ones we'll talk about specifically are the idea of topology optimization, sort of simple linear static analysis you can do, and design space exploration. Now, these are tools that simulation teams have been using for years, decades even. Now they're can be in the hands of the designers up front to inform those designs as they go. So let's look at topology optimization. Why topology optimization? Why do you want to do that? You've probably heard that name. It's a popular thing nowadays. You've probably seen a bunch of parts like this, kind of funky looking, kind of cool, and looking at those and wonder, how does that work, and what use is that? If you're not familiar with it, what it's actually producing, obviously optimized shape. Often it's optimized to reduce the mass of the part, which saves material, saves cost, depending upon the process you're using. Now, if you have a 3D printer, if you have a really cool 5-axis CNC, you might be able to take these right from the topology optimizer and go straight to manufacturing with little to no editing, maybe. But the key with any of this is that you want to use this at the beginning of the process up front to get the maximum benefit out of it. Now, the part I actually am really more excited about with it is the design guidance that this can provide. So one of the key things when I look at it as an analyst, I see these and I see it as showing me the load path. So which really just boils down to, where do I need material and where do I not need material for this part to be most efficient? Can also discover new and unimagined design possibilities. I always kind of think like I'm not a designer, but I've worked with a lot of really good mechanical designers. I think a couple things in common they have. They're really strong on engineering fundamentals, and they also have lots of good experience. But that experience might be tailored to a specific industry or a specific company or a specific type of part. And so they're going to design anything like that often. This allows them to kind of think outside the box, gives them some more examples of how they could make a design work. So we talked about why topology optimization, and we'll talk about a little bit about what it is, and I'll try to use an admittedly super simple diagram here to explain it. Overly simplistic, but if we consider this square to be sort of your design space, say this encompasses all the possible shapes, permutations, all the possible designs for this part as you start off on this design process. How do you know where you want to start on that? How do you know where the optimal design is in that? Well, a topology optimizer is you define the constraints, you kind of bound the box for it, and then you let the algorithm just search through there, and you let it go, and it'll find what it considers the optimal part, whether you're optimizing for stiffness or mass. Now, I mean, in reality, like the shape of a part, even the material of the part, all that, we all know as designers that's not the full scope of the design. There's a lot more to it. There's 100 different other choices that any engineering designer has to make when they're building a part. So I really kind of like to think of it as more not finding the optimal part, but really reducing the design space that you have to look in. It weeds out all the suboptimal areas and just limits the number of choices you have left to make. And why is that important? Because if we think about what we're trying to do, we've had a lot of talks today about the design process and everything that's involved. We're really looking at this as a time axis. At the very beginning, you have a lot of choices to make. Each successive choice you make in this design gets you in closer and closer to that final part. And if you're able to reduce up front a lot of the area you have to look in to design that part, you're just reducing the time that you can get to that end product and speed up your whole cycle. Now, I want to show you a quick example, like actual live example here. I've only trimmed out a few minutes here and there. But this is working within the context of NX. And this is using the topology optimizer in NX. There's other tools available, but this one you get to work in context, just in the CAD environment you're used to. We started in the assembly. We took a bracket and we're now choosing the design space. So we're telling the optimizer, hey, you can put material here in this green box, and then saying, don't put material in these locations because it interferes with the motor that bracket is holding, or it interferes with the bolts, or it even interferes with, you got to get a wrench in there to be able to tighten the bolts, so you need some clearance as you install this part. So you just go through and set all this up. It's pretty easy. It's a pretty simple workflow that any designer who's used to NX and used to working in CAD can do. They're going to set up the constraints. Okay, it's fixed at the bottom because there's 4 bolts to this part. They're going to work through and pick where they want to put the loads on the part and how they want to load up this. And then you'll actually see you can even, in this specific tool, you can do multiple load cases. So, all right, this was on a car. You can do a cornering case, acceleration case, braking case. You just build all those up. Then you let it know, all right, am I optimizing for stiffness? Do I want the highest stiffness? Do I want the lowest mass? This first run I'm showing here, we were optimizing for stiffness. That one took about 5 minutes to run. You can see it's pretty beefy. You're starting to see where the load path needs to be stiff. And then you can look at the performance right here in the same tool. See how the deflections and the stresses. All right, we're going to go back and say, well, no, actually, I want to reduce the mass of this part because I want as light a weight as possible while still maintaining, not exceeding some stress threshold for yield. And there's different constraints you can put on that. Now you come up with something like this, and you get sort of a typical topology optimized shape. And because you're in the same CAD environment, you can go through, you can work with this, you can make edits to this and change it, and you can, if you want, stop right there. But if we review what we're doing in our workflow here, I started with a typical sort of sheet metal bracket, and then I chose where the design space was. I said, all right, forget that, I'll tell you, like, you can put material anywhere in this space and give me the optimal part. And that's what it gives us. But you've probably, if you've heard of topology optimization, you've probably seen examples like that where you start with some sort of normal looking part and then you end up with some part like this. And if you're not the type of group that does 3D printing or really crazy machining, what do I do with this? This is useless. I'm not going to even bother with topology optimization because it's dumb. Like, nobody would ever build that in my industry. Well, that's where the second part comes in of topology optimization. And the thing I think we don't focus on enough is how it can guide design. So in this case, let's say, because again, there's other constraints to this design. Let's say it has to be sheet metal for cost purposes and for manufacturing purposes. I can actually use this part to guide myself as a designer to build a new sheet metal part that sort of mimics that shape. Again, I'm looking at where the load paths need to be and come up with a new design that can still be manufactured in pretty much the same process as I had originally, but takes advantage of topology optimization. I think that's really powerful, and that shows it can be used for anybody and with any type of design that you're doing. And if you look at the results here, I was able to reduce the mass by about 1/3 using just the straight topology optimization. And yeah, my new sheet metal part's a little heavier, still reduces the mass by about 25%. Not bad for half a day's work of the designer tooling around in CAD and playing around with this, right? So let's say I got this new design. I want to look and see how it performs. I haven't really checked the stress. I just came up with something. I thought it looked good as a designer. Like, do I need to kick this over to simulation team and let them do it? No, I can actually do this right here myself. Again, in the same context of the CAD. It's continuing that digital thread. It's staying within that unbroken. I can set up the loads. I can set up the constraints here for this new part that I designed, and I can actually analyze it and really quickly. This video specifically, for time purposes of the topology optimization, depending upon how detailed you want to look at it, it can take 5 minutes, 30 minutes. This video is actually live. We didn't edit anything out of here. So you're seeing right here how quickly you're able to set up the part, you're able to set up the loads and the constraints, and then you're able to get results. So we're looking at I believe the deflections right there. You can come through, look at the stresses, and then even go look at the animations as well. And as a designer, this is really useful because a good designer is always going to do some type of analysis up front. Often it's going to be hand calcs or an Excel spreadsheet or something. Good designers might even know FEA and be able to pull the parts in. But if you can just do this quickly to get an idea of where your part is, that's really powerful. You can see right there, we saw a little bit too much deflection right in that section. So we went ahead and added a new bracket or a new rib right there to reduce the deflection of that part. So just real quick, simple insights, simple changes. And again, we're just getting to a better and better part before we even have to move on to handing it over to the simulation team if they're gonna do any higher end analysis, or before we have to send this out to manufacture and test it to see if it's gonna break. We have a good idea up front. So if we look again, let's see where we're at. What are we doing here? We started with this new sheet metal design that we based off the topology optimization. We were able to really quickly, in about a minute, just do some quick analysis of it. And then we were add an extra little rib there just to improve the performance of this part further. But what if you want to actually look at a whole bunch of different options? Okay, we made some choices there about the holes in this part to lightweight it because we tried to match the topology optimization, right? We tried to keep this mass light, but are those holes the right shape? Are they in the right place? Is the thickness of my sheet metal correct? What if I want to explore a whole bunch of this? Do I have to do this manually? No, actually you don't. If we go back to our sort of design space and time that we were talking about, that's where a design space explorer can come in. Now, what this is going to do, it's kind of just a fancy name for automating a whole bunch of analysis runs for you, is kind of how I look at it anyway. You're already working with a parameterized part. You have variables in there. You have dimensions. You can set this up so that it will iterate through different combinations of those and start looking in your design space and just running those analyses for different combinations in there. And it's going to find which ones are feasible, which ones are infeasible, and then you're going to be able to see the performance of those and pick the best one. So we go back to the video example again. So here we're using the Design Space Explorer, again, it's built into NX here, NX CAD. So I already have CAD. It's hard to see, but I already have a bunch of dimensions in there that were already part of my part. So it's real simple to pick any one of those dimensions. You can set them up, if you're familiar with NX, set them up as expressions. Pick any one of them. Say I had a dimension of 6 millimeters, but I want to say, all right, Design Space Explorer, for that dimension, look from 2 millimeters to 10 millimeters and do it either continuously or look at like 2 millimeter increments. And you can set that up for a whole bunch of different variables. And that's basically all it is to it. You're setting up a constraints there. You're saying, the infeasible feasible is going to be whether it's above a certain stress level or not. You're going to say, what am I looking for? I'm looking to reduce the mass. And basically you hit run on this. Depending upon how many variables you set up and how many iterations you want to do on each variable, that might depend upon whether you take a quick restroom break or you go to lunch and then come back. Time may vary slightly, but it's all pretty quick. It's all going to be within a day. And you can see kind of the holes and shapes changing there as this is just automatically iterating through all these design changes, running all these studies. It's running that analysis in the background for you and coming up with the results. Now, the cool thing about this is you can go back, you can look at all the results. Often you only care about the best result, but there might be reasons why you want to maybe the optimal result, the very best design there in green. Maybe there's some other design reason that that one doesn't work, but you can look at the space of all the designs you looked at and decide, okay, that one doesn't work, but the second best or third best or fourth best here is pretty good, and it meets the other criteria that I have for this part that you can't easily put into CAD there. So it's pretty simple. And if we look again at what we were able to do there, so we started with our design that we put in the Design Space Explorer. We had a mass and we had a stress for that. And then at the end we ran, I think in this case, we ran about 104 permutations, and we were able to actually get both reduced mass and reduced stress. And if you remember from the very beginning, our topology optimized shape, that sort of funky shape that I didn't know how to manufacture with the tools I had available, was 2.8 kilograms. We're only 3% off that now, and still in with the design process we want to use for manufacturing. Now, if we take a full step back and look at the whole workflow that we went through, simulation and design. So remember, the goal was to try and find tools and methods that we could put in the designer's hands to let them inform all their design decisions with simulation. So we started with an original design, so let's scrap that. We're going to look at the design space and look at topology optimization. Came up with this shape, but decided I can't manufacture that. So, but I'm going to use that to guide a sheet metal design for me. I'm going to look at the performance of that, but one time wasn't enough. I want to look at more iterations, and I looked at 104 iterations of that and ended up with this final design here. So now you might be done there. That might be good enough. You might send that off to manufacture and test. You might send that off to build and install. But you might also want to look, then quickly just move on to higher end analyses. So again, a lot of the things today, we're trying to shift everything to the left on the design cycle. Actually, it's left for you guys here. That's my left. But we're trying to shift everything to the left. We're trying to get everything faster. So you were able to do the single part analysis quicker. You were able to look at more concepts. You were able to build a better design, try and get that right the first time, which means you can move more quickly to assembly level analysis. You can move more quickly to the high-end multi-physics. And that's where everything is kind of going nowadays. For instance, this is just sort of an example of all the types of analysis the simulation services team at Maya has expertise in. And this is what we're seeing more and more. Customers are moving to this level to maintain, to be competitive, to be more competitive, to stay ahead of everybody, and to get better products out. Now, you're sometimes not even going to get to this level if you can't get past that first hurdle and all the time needed to analyze that first part. So that's the whole goal. Shift everything to the left, give tools to the designers as so they have a simulation-driven design, and then be able to move to higher order things to make your designs better. I want to say thank you for your time today. If you're interested actually in talking more about your workflow, if any of these tools are of interest in you, or talking about like just higher end analysis in general, how that might help, scan over there. I'm open for a 30-minute call. Would love to talk to you. I love talking about this stuff and kind of chatting with people and helping them find efficiencies in their process. So with that.
Thank you, John. We do have time for a couple of questions, depending on the length and the follow-ups. Anyone have any questions? Hey, great.
Hi. Thank you very much for the presentation. I have a question about the topology optimization. So when the simulation makes changes to the part, how do you know, like the base part? There should be, I guess, a base part from the design, right? How much in the topology optimization is it changed on the part, and how do you know how much of the base part you want to keep and how to constrain that in the topology optimization?
It's a good question. You can do it two ways. The way I actually did it here, I had a base part, but that's not what I fed into the topology optimizer. I fed it like that green box and just said, you can put stuff anywhere in this green box. You can also do it where your green box effectively is a part to begin with and say, just take this and remove material. So you can do it either way. In this case, I just gave it a box and where to keep out.
Great question. Any other questions? Go around the pillar. Nope, I think we're good. Please give it
All
up
right.
for John, everyone.
Thank you.
Thank you.